Hello again, and welcome to our series on the wonders of astronomy. The slide just before this indicated this was program 1. That's my mistake. It was actually program 7. This one is on extraterrestrial life. We are celebrating the 400th anniversary of Galileo first turning his telescope towards the heavens, and this year is called 2009 the International Year of Astronomy, and we are inviting you to participate in various astronomy programs, and I'll have a brief slide at the end of this to show you how you might do that. So for now, let's begin, and as I said, this celebration is because Galileo 400 years ago turned this very simple telescope towards the heavens, and he actually began to see things in a scientific way. Without mythology and applying true science to the art of astronomy. Now, this program is on extraterrestrial life. I will not be talking about UFOs, so I'm sorry if you have some particular preference either for or against UFOs. I'm not going to address that particular situation. We will be looking at the scientific basis for life out there rather than UFOs. So if you have some particular opinion about them, I'm not going to change that at all. Now, we actually got off on the wrong foot when we first started looking for life out there. This gentleman here at the telescope is Percival Lowell. He was a very rich astronomer, amateur astronomer from the Boston area, and in the 1900s he read about some Italian astronomers who thought they had seen channels on Mars. That was translated as canals, so that got him very interested. He started looking, and he actually found what he thought were the system of canals on Mars. He wrote quite a few articles and books on this and talked about the civilization on Mars that must be trying to get water from the poles down to the desert regions to have crops. Of course, he was wrong. This is what Mars actually looks like. This is the same view of Mars with a modern telescope, and as you can see, there are simply no canals on Mars at all. Today we have very good close-ups. This is a space probe looking in great detail. Now, there are such things as canyons. This is Mariner Valley, as it's called, which is a tremendous canyon that dwarfs the Grand Canyon. This canyon actually would stretch from Los Angeles to New York City if it was put on the United States. But as you can see, there are no canals at all. There's no indications of any intelligent life there on Mars. Now, we have had these rovers on Mars since 2004. They're called Spirit and Opportunity, and they have been looking around Mars in great detail, examining the rocks and everything. They've found signs that there definitely was water on Mars at one time. Mars at one time was a very wet planet. Apparently today all that water is now frozen in ice underneath the surface. There's no apparent water on the surface right now. In fact, the atmospheric pressure is so low on Mars that it would just evaporate immediately if it did exist. So basically we can say that there right now is apparently no detectable life, definitely no intelligent life on Mars except for our rovers. Now, we do have some signs that there may have been life on Mars at one time. Apparently, about 15 million years ago, this particular chunk of rock was blasted off the surface of Mars by an impact. And it landed in Antarctica about 13,000 years ago. Well, the first thing you're going to ask is, how in the world do we know that that rock comes from Mars? There were very small cavities inside the rock, and when the atmosphere in those little cavities was examined, it was exactly the atmosphere of Mars. And we know what that is because we've had probes there on the surface of Mars. So we know that this rock definitely did come from Mars. One thing that we found that was very interesting is these carbonate globules inside of that rock. That's usually a clear indication on Earth that life is present. Another thing we found is this interesting fossil right here. Now this fossil, some say is just a mineral, but to me it definitely looks like some bacterium. This was taken with a scanning electron microscope, so this is magnified millions of times. It's extremely small, but many people think this is some indication that at least primitive life was there on Mars sometime in the past. Now, we have been active in doing something about communicating. Back in 1974, we took the giant 1,000-foot radio telescope at Arecibo in Puerto Rico, and we sent this message. Now, this might not mean much to you, but the experts say if some intelligent civilization actually decoded this message, they might figure out where the message came from. The problem is they sent it to a star cluster called M13, which is 25,000 light years away. That means we should expect a response from the message in about 50,000 years. Now, I'm personally not waiting around for that. We are, though, listening. We think that that's probably the best bet, is just to listen to see if there's anything out there. And the program that's set up to do that is called SETI, the Search for Extraterrestrial Intelligence. This is nowadays a nonprofit organization. It's not sponsored by the government, but it's searching for intelligent life out there. One of the heads of that is Dr. Frank Drake, and I'll show you his famous Drake equation later on in this presentation. What they're doing right now is setting up a series of these dishes. Each dish is about 10, 15 feet in diameter, and they're setting a whole array of these up in Hat Creek, California. When they're finished, they'll have about 350 of these dishes there in Hat Creek, and they'll span a distance of about 1 kilometer. And hopefully, they say within 25 years, they hope to actually detect life by hearing an intelligent signal. Now, they're also trying what they call an optical SETI, rather than listening over radio bands, because radio spans such an enormous band, we have to have a lot of detectors, but light is in a very narrow part of the electromagnetic spectrum. So, it's very easy for an intelligent civilization, perhaps, to communicate using light waves. And so they're looking for strong lasers out there. Nothing, of course, has been detected yet. And these telescopes that they're using basically are what we might call second-class telescopes. They're not the large research telescopes. They're telescopes that have passed their prime, but still are useful to look for such things as laser beams. Now, so, well, where do you look? Well, this is the famous, what we call HR diagram, or Hertzsprung-Russell diagram. I'm not going to spend a lot of time on it. It's really quite simple. We have brightness along this axis here, and then going across, we have temperature. From very bright, hot stars to very dim, cold stars. So this is cold, this is hot, this is dim, and this is bright. The stars up here, the O, B, and A type of stars, don't live long enough, we think, to produce life. We know that it took life approximately 3 to 4 billion years to evolve on our planet. So we think we need to look at a star that's at least 5 billion years old, if not older. That means we're going to be looking here at these F, G, and K stars. We happen to live on a planet that orbits a G-type star. Our sun is a G-type star. So this is the area that we want to look at. Now, for years, many astronomers said, well, this M stars, these red dwarfs, are simply too cold to have any planets with life on them. We're beginning to change our thoughts on that now. We've found some M-type stars that do have planets close enough to be habitable. In other words, close enough to have water in a liquid state on the planet. So we may actually have extended the range at which we think we may be able to find planets around stars. So there's definitely a lot of opportunity out there. Now, there are also in the cosmos many of the building blocks of life. We have many amino acids. In addition to these molecular clouds where there's nitrogen, hydrogen, and oxygen, we have amino acids. We have alcohol, actually. They recently discovered a huge cloud of alcohol out there, enough to supply the United States, or actually our whole planet, with plenty of drinks for thousands of years. But it's too far away to get, and too diluted anyway to make any sense. It's easier to make it here. But all life on Earth is derived from basically just 20 amino acids. And many of these amino acids are already existing in the meteorites in outer space. And we have about 10 tons of material per day coming into the Earth in terms of micrometeorites, dust. And so we're constantly building the Earth up with these elements, some of which might have life in them already. As we look out, we see these giant pillars. These are called the pillars of creation, and this was taken by the Hubble Space Telescope. These are giant pillars of dust and gas which are forming new stars, and you can see these little protuberances coming off here. These are actually new star systems emerging from the cloud in which they were born. To get an idea of the size, our entire solar system could fit in the tip of one of these little spurs coming off. This entire cloud is 4 light years long. So these are enormous things, and they contain all the elements necessary to produce not only stars, but planets as well. Now, within a galaxy such as we live in, there are typically 200 to 400 billion stars. And we know that there are at least, at a minimum, 200 billion galaxies out there. So it's kind of hard for me to imagine that we are the only ones around. There must be somebody else out there when you just look at the numbers alone. Because of this, NASA is very seriously looking at the idea of life existing out in the cosmos. And they've started a new science called astrobiology. In fact, they've actually established an astrobiology institute within NASA. And they're holding annual meetings now. They're looking at the combining various sciences. The science of astrobiology contains astronomy, cosmochemistry, organic chemistry, molecular biology, and all these others. Combining these to look at the rationale for life actually being out in the cosmos. They have a lot of encouragement. In the last 25 years, we've begun to examine the bottom of the oceans, where the oceans are being torn apart and where there's volcanic activity. And what we found is that there's life down there, life existing in a place where there's absolutely no light at all, no energy from the sun coming in. And yet we find these giant tube worms, we find shrimp, and we find many bacteria. These are existing through a process that we call chemosynthesis. This is a process in which the organic material is being converted into energy. So, and the primary chemical is hydrogen sulfide. This propels the chemosynthesis the same way that sunlight provides photosynthesis on the surface. Now, all the life forms on the surface of the Earth use photosynthesis to live. The sunlight striking the green plants through photosynthesis creates sugars and starches in which we higher life forms live on. We are actually propelled ourselves by solar energy. You are propelled by solar energy through the process of photosynthesis. But now we have another process, an entirely separate process called chemosynthesis. So this may exist in other worlds as well, not only ours. In addition, on the surface we find that there are many things such as bacteria that exist in extremely hot conditions or extremely cold conditions. From the Antarctic all the way to the hot springs here in Yellowstone Park. The colors are created by various bacteria living in the various temperature ranges in these very hot pools. This water is just about at the boiling point, and yet we see these extremophiles living there very happily. So from the deepest cold to the hottest temperatures on the face of the Earth, we see creatures living there. Now, to me, one of the most encouraging things is the retrieval of the camera that was on the Surveyor 3 spacecraft. This is a picture of the Surveyor spacecraft with one of the Apollo astronauts standing next to it. This particular vehicle was sent to the moon 30 months before Apollo 12 arrived, and it had conducted experiments, and it had a camera on board to see what the surface might look like. After exposure for 30 months, the astronauts were asked to take the camera off the vehicle and bring it back to Earth. When they did that, they found that there were bacteria inside of it. And when they scraped off those bacteria and put them in a culture, they began to grow again. So here is Earth-type bacteria that we thought was very fragile, that in fact survived the trip all the way to the moon in a vacuum, then lived for 30 thermal cycles, the extreme cold and the extreme hot of the lunar days. And when they were brought back to Earth, they lived again. So life is tough. We can say that not only is life tough, it's tenacious. It can really grip things. So on planet Earth, under the most extreme conditions, we find life existing. That gives us great encouragement that there's life out there. Now, many people today are talking about the idea of panspermia, which simply says that life, in fact, exists almost everywhere in the cosmos. When giant stars explode in supernovas, they typically shatter many of the planets. And those planets, if they had life on them, would spread that life out throughout the whole universe. And so perhaps comets and meteors are bringing life to Earth all the time. So that's the idea, that perhaps comets and meteors actually seed the entire cosmos with the elements of life itself. And it doesn't take then much at all for life to take hold on a planet once the conditions are just halfway credible for life. Now, I mentioned before the Drake equation, and this is something you can have a lot of fun with. I happen to have fun with it. In fact, there are actually websites in which you can just go and Google a Drake equation, and it will provide a calculator for you. Or you can just do this yourself very easily. This is a modified form of the Drake equation. Dr. Drake early on was asked to give an estimate of how many civilizations might be out there in our own Milky Way galaxy. And on the way to the lecture, he kind of thought about it, and he said, well, really, it's a simple addition is all it is. The number of intelligent civilizations that could be communicating are, and what he used is the rate of star formation. Most people now modify this equation just to say the number of stars in the galaxy. This is an easier way to use it. So This number R would be 200 billion. So you can plug 200 billion into the equation there. Then the next element in the equation is the fraction of those stars that have planets. We now know that at least half the stars seem to have planets. Planets are very common to the formation of new stars. So you can use a 0.5 here for this second term. So I've already provided you the first two terms. Now this is where you can apply your own judgment to things. The next term is the number of those planets that might be Earth-like. Now in our own solar system, we know that there's only one Earth-like planet in our solar system, and that happens to be planet Earth. So you can say that's 1 out of 8 major planets. Or I like to use a number of 0.1 here. 1 in 10 might be an Earth-like planet. Now of those Earth-like planets, what are the fraction that might actually produce life? I think that fraction is pretty high. Many people are speculating. These new astrobiologists are actually speculating that if you get an Earth-like planet, you're going to get life on it. It's almost a given. But I'm a little more conservative than that, so I usually use a much smaller number. Now, of those Earth-like planets that actually produce life, how many produce intelligent life? Fi is the intelligent life. Now we know on this planet it took quite a while for intelligent life to evolve. Some astrobiologists are saying that if you get life on a planet like planet Earth, eventually it will become intelligent. I don't know about that. I put a fraction on that, maybe just 1% might actually produce intelligent life, because it has to be in a stable environment long enough for life to evolve into intelligent life. And finally, the last term is those planets with intelligent life that can actually communicate. Now, we human beings have been on this planet for quite a while, and yet it's only within the last 100 years that we've been sending radio signals out into space. It's only a little over 100 years ago that we actually developed radio communication. So our signals have only been going out for about a little over 100 years, which means anybody within 100 light years of planet Earth might know we're here, but outside of that, they would never know we exist. So we can conclude from what we've been saying that certainly all the building blocks of life are out there in the cosmos, and they're plentiful. We can look at the Drake equation and say that there's a pretty good percentage possibility that life exists. When Dr. Drake put his numbers in, and I think Dr. Drake knows a lot more about this science than I do, he came up with a number of 10,000 intelligent civilizations in our own Milky Way galaxy. I tend to be a lot more conservative. When I put my numbers through, I come up with about 20. So you put your own numbers in there and see what you come up with. You might find it quite interesting. And we've also found out that life is very tough. As we look at the extremes here on Earth, we find life everywhere. So the big question then is, why haven't we actually heard anything? Why is it so difficult to detect any other life out there? So what I'd like to do next is actually talk about the difficulty of both communicating and traveling just within our own galaxy. If we were trying to communicate with somebody on the other side of the galaxy and we said, let's go out for pizza tonight, that signal would take 100,000 years to go across the galaxy. So this guy would say, sure, but tonight was 100,000 years ago. And of course, it's going to take his reply 100,000 years to get back to us. Now, as I said, Dr. Drake estimated that there were 10,000 civilizations in the Milky Way galaxy. If we said there were as many as 1 million civilizations in our galaxy, we would find that it still takes 150 the closest one would be 150 light years away. That means two-way communications would take 300 years. So you can't exactly have a stimulating conversation if it takes 300 years. So communication is very difficult on the kind of scales we're talking about, because those radio waves travel at the speed of light, and it just takes time for them to get to wherever they're going. Now, as I said, my estimate using the Drake equation would be about 20 intelligent civilizations here in our Milky Way galaxy. So here I'm taking a picture of the Milky Way galaxy, an artist's conception of the Milky Way galaxy, and these red dots represent 20 civilizations beyond our own. And here we are down here, and we've just looked just barely in our own neighborhood. We haven't looked out very far at all, simply because our detectors are not that good. Even our huge telescopes are not that good. So if this particular civilization here was listening, it's about 10,000 light years away. Our signals have only gone out 100 light years. So it's going to be quite a while before they even know we exist. And then if they sent a signal back, it would take another 10,000 years. So that's why it's so difficult. That's why we're having problems detecting anybody else. Even if they're out there, the space is so immense that their signals simply haven't reached us yet. Now, let's talk about travel. Say we want to go to a nearby star. An interesting star is Sirius. Sirius is 8.7 light years away, so we might get in a rocket, and this rocket, if it was traveling at twice the escape velocity, that's 22 kilometers per second, we've never been able to achieve that kind of velocity in any probe that we've sent out, but we could do it if we had the will to do it, if we wanted to build a large enough rocket and burn the fuel for long enough. We could get up to those speeds. At that speed, it would take us 120,000 years to reach Sirius. Now, and that means your spaceship cannot simply be a spaceship. It has to be a city. It has to be a small planet unto itself, because it has to sustain life through 5,000 generations. Now you say, well, let's not go to Sirius, that's too far. Let's go to the nearest star. The nearest star is only half that distance. So you can cut these numbers in half then. It's only 60,000 years to get there. And you only have to sustain life through 2,500 generations. Still, you can see the problem. You're not talking about a spaceship. You're talking about a mini planet that would have to be sent to get to these nearby stars. It's just that difficult because of the immensity of space. Now, you may have heard of the term wormhole. That's not referring to those little creatures in the ground. Wormholes are something that Einstein's general law of relativity predicted might be a possibility. And basically what Einstein said is that if you look at space-time as a fabric, you might actually be able to bend it around. And here we see space-time actually bent around like so. And you could then take a wormhole, which is like a black hole, and dive through that wormhole and go from point A to point B as a shortcut. Rather than going all the way around, you can simply make the shortcut. Now, theoretically, this would be possible. We have no concept at all right now of how we would ever produce a wormhole, how much energy it would take, or how you could ever do it. But if you could do it, this might be a possibility of going to either other parallel universes or to another point within our own universe. But as you can see, ordinary rocket travel as we know it just doesn't make any sense. So in the end, you know, what can we say? There's 400 billion stars probably in our own galaxy. And we know that there's at least 200 billion other galaxies out there. And so I would end not with a conclusion, but with a question, the same one that Wernher von Braun posed to us. Are we the only living things in this immensity? I tend to think not. So that's my opinion, and I hope you've come to some interesting conclusions as you look through this. I encourage you to try a Drake equation, see the kind of numbers that you yourself come up with. Now, in this series of programs, this being the last one, I want to again invite you to participate in some form of astronomy. There's many open houses being held this year. Hopefully you're enjoying these TV programs on astronomy. And there's also star parties. Star parties are parties in which the organizations have set up telescopes and invite you to come and simply look through a telescope. No charge, just look through a telescope and see what they happen to be observing on that particular night. Now, how do you do that? You go to these websites. In northern Vermont, you can go to the Vermont Astronomical Society at vtastro.org. And in southern Vermont, you can go to the Surveyor website, the Southern Vermont Astronomy Group at sovera.org. And they will give you the times and places of these star parties. It's hard to plan a star party very far in advance because it depends a lot on the cloud cover. So there's very short notice on these things. That's why you have to use the websites. If you have any questions for me, I again invite you to contact me at astromanvt@gmavt.net. Thanks for your interest in astronomy, and I hope to hear from you.